to my YouTube channel. Okay, can everybody see my slide that says properties of acids? Just want to be 100% sure. All right, thanks, Warren. Thanks, Kristen. Okay, my slide that says properties of acids. So let's get started here. We're continuing on with chapter 4, and we just finished molecular equations, total ionic equations, and net ionic equations, and now we're on to acids and bases. First, we're going to look at some properties of both acids and bases. It says here that acids have a sour taste. Now, I wouldn't go around tasting any acids in the lab. That would be a big no-no. But if you've ever tasted vinegar, it has a bitter, sort of sour, a bit of a bite to it. And that is from acetic acid, which is an acid. Now, acetic acid is not a strong acid like sulfuric acid or hydrochloric acid, but it is an acid. Also, if you've ever gotten lemon juice in your eye, you know that that stings too. And citrus fruits like oranges, lemons, and limes, they contain citric acid. Next, it says that acids cause color changes in plant dyes. I'm never going to ask you about that. What it means is that soil pH, so the relative acidity of soils, can have an effect on the color of different plants like hydrangea and things like that. Other interesting things that acids can do is they can react with metals. You can simply mix an acid like hydrochloric acid with a metal like magnesium, and it'll produce hydrogen gas, which is a flammable gas. That's what's going on right here. This strip of metal here, that's magnesium, and it's in hydrochloric acid, that's aqueous. You can't see it, but in here, it's forming magnesium chloride, which is aqueous. So it's homogeneous. It's a homogeneous solution. But the bubbles here are from hydrogen gas that's being liberated. You can also react an acid like hydrochloric acid with a carbonate, like calcium carbonate, to form calcium chloride, but you can also form carbon dioxide gas in water. And it says here that aqueous acid solutions conduct electricity, especially strong acids, right? Because strong acids are strong electrolytes and weak acids are weak electrolytes. We saw that a few slides ago. With respect to bases, if we think about the properties of bases, it says here that bases have a bitter taste. So oftentimes foods that have bitter tastes will be basic. Now when it says feel slippery, if you were to take a strong base like sodium hydroxide, I certainly wouldn't touch that with my skin. But if you were to touch it with a glove, for example, it's slippery and it has the sort of a consistency of like a liquid soap when it gets on a glove. Now, again, I wouldn't touch a strong base with my hands. But many soaps contain bases, and that's why many soaps have that slippery feeling. Again, they also cause color changes in plant dyes. Same rationale for the acids. They can affect the relative acidity or basicity of soil and thus the color of the plant. And aqueous base solutions can conduct electricity. Why? Because if we have a strong base, it's going to be a strong electrolyte. It's going to break apart completely into its cation and anion. Well, a long time ago, when people were first learning about acids and bases, a scientist named Arrhenius came up with the first definition of what an acid is. It's a primitive definition compared to what we know nowadays, but it is still a good definition, and it covers most acids. It says here that an Arrhenius acid is a substance that produces a proton in water. Now remember that I told you earlier this evening that when you have H+, we call that a proton. So then you might be wondering, well, why do you have hydronium? That's H3O+. This is called hydronium. You might be wondering, why do we have hydronium in brackets? We're going to look at that in a second. But what happens is that the Arrhenius acid, HCl, donates or produces the H+ ion that comes from the hydrogen in the HCl. But the definition of an Arrhenius base is a substance, anyhow, I'll get back to the definition of Arrhenius base in a second. But anyhow, the water accepts that proton, and the H+ doesn't just hang around next to water. it actually combines with the water to form the hydronium ion, and of course we're left over with the chloride. Now, a little bit more about that hydronium in a second. First, I want to talk about an Arrhenius base. And the definition of an Arrhenius base is a substance that produces hydroxide in water, things like sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, et cetera, et cetera. So if we look at something like sodium hydroxide, I'll write this down here. You can see how when we put sodium hydroxide in water, it breaks apart into the sodium cation and the hydroxide anion. But the problem with this definition with a molecule like ammonia is that ammonia doesn't have a hydroxide in it, right? It's just NH3. But the reason that ammonia can be considered an Arrhenius base is because it produces hydroxide when it's put in water. How? Because ammonia is a base, it accepts a proton from water, which actually behaves like an acid in this case. When the ammonia takes on the proton, it becomes an ammonium ion, ammonium, and you're left over with hydroxide. So you see how even though ammonia doesn't contain hydroxide, it produces hydroxide in water, and that's why it's considered a base. Again, the hydronium ion is nothing more than a hydrated proton. When we look at a broader definition of acids and bases, we move on to the Bronsted theory of acids and bases, or the Bronsted definition of acids and bases. It's a little bit simpler definition, but even though it's simpler, it actually covers a broader range of acids and bases. It says a Bronsted acid is a proton donor. Remember, a proton is H+, and a Bronsted base is a proton acceptor. Well, how do I know that this is a Bronsted base? Because it accepts the proton from the water. So that means that the ammonia here is behaving as a Bronsted base. I'll just leave that out. I'll just say it's behaving as a Bronsted base. This is behaving as a Bronsted acid because it's donating a proton. And then we're left with ammonium, which is considered an acid, and hydroxide, which is considered a base. Now, if you're wondering, why did you write acid and base over here? Because remember, this is a reversible reaction. So if we think about the reaction going backwards, okay, in the reverse direction, just imagine it was going in that direction. The ammonia would be donating the proton to hydroxide to form water. So since ammonium is donating a proton in the reverse direction, it's considered an acid. And since the hydroxide is accepting a proton in the reverse direction, it's considered a base. There are many ways that we can classify acids. We've already seen strong and weak acids. Strong acids are like sulfuric acid, hydrochloric acid, nitric acid, perchloric acid. Weak acids are like hydrofluoric acid, acetic acid. But another way that we can classify an acid is based on the number of protons it contains. Say, for example, we were to compare these three right here, and I'll write them up at the top. And they're on here, but I'll just try to make it a little simpler. If we were to compare HCl versus H2SO4 versus H3PO4, they're all acids. The first one is hydrochloric acid, the second one is sulfuric acid, and the last one is phosphoric acid. What's the Bronsted definition of an acid? It's a proton donor, something that donates a proton. When we look at the HCl, the hydrochloric acid, it only has one proton to donate. If we look at sulfuric acid, it's got 2 protons to donate. And if we look at the phosphoric acid, it has 3 protons to donate. The classification of these are monoprotic for 1 proton, diprotic for 2 protons, and triprotic for 3 protons. We have some other examples of monoprotic acids besides HCl. Again, HCl and nitric acid are strong acids. That's why they both have irreversible arrows, and that's why we can say for both of them that they are strong electrolytes, because they're strong acids, right? A strong acid is going to dissociate completely into a proton and its anion. This is another way of writing acetic acid. So if you need to write that down here, this is acetic. It comes up a lot in chemistry. Acetic acid. Acetic acid is a weak acid, and therefore it's a weak electrolyte, exemplified by this reversible arrow. Is it going to form some of the ions? Absolutely, but not nearly as many as the strong acid and the strong base will. In fact, the dissociation of acetic acid is only around 5%. Okay, so it's 95% acetic acid and only about 5% the ions. So that's why it's a weak electrolyte. A diprotic acid, like sulfuric acid, has 2 protons to donate, but it doesn't donate them with an equal strength. The first proton is completely removed by complete dissociation. However, once you form this anion, the hydrogen sulfate anion, it can release this proton. Okay, the hydrogen sulfate ion can behave as an acid, but think about it. We know that opposites attract, right? Positive charges are attracted to negative charges. So if the hydrogen sulfate ion already has a negative charge on it, why would it want to give up a positive charge, right? That's just going to produce something that's even more negative. And so that is why the first proton that's donated is donated irreversibly, but the second proton, the hydrogen sulfate ion, is not that eager to give it up. And so the hydrogen sulfate is a weak electrolyte. It's a weak acid, whereas the sulfuric acid, when it has the 2 protons, is a strong acid. Now, phosphoric acid is actually a weak acid, not a strong acid anyhow. So it's weak no matter what. But the idea is this: as we go from H3PO4 to H2PO4 minus to HPO4 minus, as the anion gets more negatively charged, it's going to have a lesser of a propensity to give up a positive charge. Why? Because it's already negative. It's saying, I'm already negative. Give me all my positives. I want to hang on to them. Okay? Give me a thumbs up if you just follow the concept that I'm going over here. Strong and weak electrolytes. And if a diprotic or a triprotic acid gives up a proton, once it's given up a first proton, it's going to have a lesser propensity to give up the second and a lesser propensity to give up the third in the case of a triprotic acid. Is anybody with me? Okay, thanks. Okay, anybody else? I hope my students are there. Oh, maybe my Teams is timing out or something here. Just give me a second here. Oh. All right. Now you need to memorize everything on this slide. Some students do it by flashcards. Some students do it by, I don't know, repetition. But you need to memorize all of the strong acids. There are 6 of them. And you need to memorize these weak acids. There are many more than 4 weak acids. There are hundreds of weak acids. However, these are the 4 that you need to know. So you need to know hydrochloric acid, hydrobromic acid, hydroiodic acid. Notice that all of these are what we call halo acids, right? Because they come from the halogens, chlorine, bromine, and iodine. But notice that hydrofluoric acid is not a strong acid. It's a weak acid. After that, we have nitric acid, sulfuric acid, perchloric acid. So those are the 6 strong acids. And the 4 weak acids that you need to know are hydrofluoric, nitrous acid, phosphoric acid, and acetic acid. Well, let's look at a practice problem. Question 4.3. I'm going to give you a second to think about this one. It says classify each of the following species in aqueous solution as a Bronsted acid or a base. Remember that a Bronsted acid is an H plus donor and a Bronsted base is an H plus acceptor. All right, I'll give you a couple seconds to think about that. All right, let's take a look at the first one. We have HBr. Could anybody tell me, would that be a Bronsted acid or a Bronsted base? Would HBr be a Bronsted acid or a Bronsted base? Thanks, Christina. Yeah, HBr would be a Bronsted acid, right? Because we know that HBr is a strong acid. It was on the last slide. Could anybody name this anion over here? NO2 minus 1? Could anybody name that anion?
Nitrogen dioxide?
No. Nitrogen dioxide would be a covalent compound. So this is a, no, it's not nitride. So if we have NO3 minus, that's nitrate, right? And if we lose an oxygen, this is nitrite. Okay, so this is a nitrite. N3 minus, that's nitride. And nitrogen dioxide would be this. It's got no charge, nitrogen dioxide. All right, so this is a nitrite anion. And since it has a negative charge, thanks, Christina, it would be considered a Bronsted base, right? It would accept a proton because it's got a negative charge. This anion here, could anybody name that? HCO3 minus?
Bicarbonate?
It's the bicarbonate, that's right. If you have CO3 2 minus, that's a carbonate ion. And if you have HCO3 minus 1, this is a bicarbonate. Bicarbonate, or you can call it hydrogen carbonate. Either way is fine, but bicarbonate's what's usually used. Now, what about bicarbonate? What do you think there? Would that be a Bronsted acid or a Bronsted base? Yeah, Christina, I agree with you, and Anthony, I agree with you, both of you, that it could accept a proton for sure. It could accept a proton to become H2CO3, right? Carbonic acid. But also, it could lose a proton to give you H plus CO3 2 minus. So the answer for bicarbonate would really be either, right, Alec? It would be both. We'd say that bicarbonate, depending on, and if you're like, well, which one is it more? The answer would be depending on the situation, it could be either, okay? So this will put acid or base, and then if you want to write in depending on the situation. And if you're wondering, well, would you ask me that on an exam, in such a way that I won't be able to answer it? Of course not. I'll always give you a question that you're able to answer. I'm not going to try to trick you or something. Well, let's talk about a neutralization reaction and what a neutralization reaction is for a second. If you have an accident in the lab, and accidents in the general chemistry lab are pretty rare where we spill large quantities of an acid. But if you were to, say, for example, spill a really strong acid on the floor, like a big bottle of sulfuric acid, what would you do? Would you put water on it? Probably not, because that would just dilute the acid and it could create a lot of heat. Because when we combine acid and water, we can generate a lot of heat. In fact, in French, we say acide dans l'eau, bravo, which is acid in water, bravo, l'eau dans acide, suicide. So you do it the other way around and you can die. So what would you do if you spilled a lot of acid on the floor? You would combine it with a base, because when you combine an acid and a base, you get a salt plus water. Now notice when it says salt, it doesn't necessarily mean table salt. Okay, it could be, but a salt simply means that you get something that's ionic plus water. Here's an example, and in this example, what do you know? You end up producing table salt. But here's a molecular equation for what happens if you combine hydrochloric acid and sodium hydroxide. The proton combines with this anion to produce water. And this cation combines with this anion to give you sodium chloride, table salt. It's in an aqueous solution, mind you. But anyhow, so we take the strong acid and strong base, both of which are, dangerous to our skin, for example, and we end up with nothing more than a solution of salt in water. You need to have this memorized, that a neutralization is acid plus a base gives you salt plus water. Again, not necessarily table salt, but an ionic compound. The next equation is simply the total ionic equation. We break apart everything that's aqueous into its ions, which is done right here and here. But notice that water is not aqueous. Water is a liquid, okay? Does not ionize. What's the last equation? It's our net ionic equation. A student asked me, how do we get to the net ionic equation before? Again, we cross out anything that appears on the opposite sides of the arrow. We have chloride as a reactant. We have chloride as a product, so we cancel that. We have sodium as a reactant. We have sodium as a product, so we cancel that. What are we left over with? H plus. Can you guys see my screen, or did it go away? Okay, good, thanks. Plus hydroxide produces water. That's our total ionic or net ionic equation. Is hydrogen ion, the proton, plus hydroxide gives you water. What you're going to find is that for a neutralization reaction, the net ionic equation will almost always be the same. Okay? This will be the net ionic equation for a neutralization reaction. So if I asked you a multiple choice question on the next exam and I said, which one of these equations represents the net ionic equation for a neutralization reaction, you would select the one that's a proton plus hydroxide gives you water. What about a neutralization reaction that involves a weak electrolyte, meaning a weak acid or a weak base? Let's take a look at what happens when we combine a weak acid with a strong base. we still end up with the salt and water, but notice that we have equilibrium arrows instead of an irreversible arrow. HCN is hydrocyanic acid. It's not a strong acid. It's a dangerous acid, but it's not a strong acid. In fact, it's a gas when it's not in solution. That's what they used to use in the gas chamber in California as a poison. Anyhow, when you combine hydrocyanic acid with sodium hydroxide, we end up with something that's a little different than when we combine sodium hydroxide and hydrochloric acid. Let's take a look. The proton here is going to combine with, the strong base is going to dissociate completely into its ions because it's aqueous. But since this is a weak acid, it is not going to dissociate completely into its ions in the total ionic equation. It's their molecular equation. So we have the only thing that cancels out on both sides of the total ionic equation is the sodium ion. So our total ionic equation, when we combine a weak acid and a strong base, is a little bit different. Now, in our net ionic equation, we get our weak acid plus hydroxide gives us our anion plus water. So when we go back to this slide and we see this general equation, that would be for the combination of a strong acid and a strong base. Let's try an example. It's the best way to practice this. I want you guys to take a few minutes and try to write a molecular, ionic, and net ionic equations for the following acid-base reaction. HBr plus barium hydroxide. And we're going to make the assumption that the HBr is aqueous and the barium hydroxide is aqueous. Now remember, hydrobromic acid is a strong acid, and when it comes to bases, any hydroxide of a group 1A or 2A metal is considered strong. So since barium is a group 2A, barium hydroxide is considered a strong base. All right, since HBr is a strong acid and barium hydroxide is a strong base, we're going to put an irreversible arrow and we're going to produce a salt plus water. We can start by writing our water. What's our salt going to be combined or composed of? Barium and the bromide. Remember that since barium is in group 2A, it's barium 2 plus, and bromide is always -1. So that means the formula for barium bromide would be BaBr2. And it's aqueous. I'm not going to go back to the solubility table, but if you want to, you can go back and prove it to yourself. Now we need to balance out the equation. I have 3 hydrogens here. Why don't we start by balancing the bromines? I have 2 bromines here, so I'm going to put a 2 in front of the HBr. Now I've got a total of 1, 2, 3, 4 hydrogens. So I'll put a 2 in front of here. And now everything is balanced. And that is my molecular equation. Okay. Next, we're going to write out the total ionic equation. So that means that everything that says AQ, we're going to break it apart into its ions. So everything except water. For our 2HBr, we've got 2H plus ions in solution, plus 2 bromides in solution, plus we have a barium in solution, plus we have 2 hydroxides in solution. Now I'm on the barium bromide. On the products, we've got a barium ion in solution, plus 2 bromide ions in solution, plus 2 H2O. Could anybody tell me what the spectator ions are in here? Thanks, Kristen. It's the barium and the bromide. The barium ion and the 2 bromides are the spectators. They're the same on both sides. So now I can write out my net ionic equation, which is 2H plus aqueous plus 2 OH minus aqueous produces 2. I forgot to put a 2 there, didn't I? 2 H2O liquid. We can simplify that to 1H plus hydroxide produces H2O. Right? All I did was divide all of that by 2. And so we see, again, when we combine a strong acid and a strong base, we end up with the same net ionic equation that we did when we combine a strong acid and a strong base here. Let's write a molecular ionic and non-ionic equation for this acid-base reaction. Sulfuric acid plus potassium hydroxide. Sulfuric acid is a strong acid and potassium hydroxide is a strong base. I'm going to do this one a lot quicker. So sulfuric acid is strong, potassium hydroxide is strong. They're going to combine to give me water plus potassium sulfate, K2SO4, which is soluble. I don't have to look it up in the solubility table because I have most of them memorized, I think. How did I know I was going to get potassium sulfate? Look, all I did was combine the H with the OH to give me water, and then I combined the sulfate with the potassium to give me potassium sulfate. Now this equation isn't balanced. We need to do that. We have 2 potassiums over here, so we need to have a 2 here. And then we need to have 2 over here because the oxygens, here we have 6 and here we have 6. Okay, good. Everything's balanced. This again is my molecular equation. Let's write out our net ionic equation. In the sulfuric acid, we're going to completely dissociate it into 2H plus aqueous plus SO4 2 minus, which is a sulfate ion, aqueous, plus 2 potassiums, aqueous, plus 2 hydroxides, aqueous, which produces potassium sulfate, which breaks apart into 2 potassium plus, aqueous, plus sulfate, 2 minus, aqueous, plus 2 H2O liquid. Cross at our spectator ions, which are the potassium and the sulfate, and look what we're left over. In our total ionic equation, we have 2H plus aqueous plus 2 OH minus aqueous produces 2H2O liquid, which again, we could divide all of that by 2 to give us H plus OH minus produces, oops, H2O, like that. All right. We can also have neutralization reactions that produce a gas. For example, when an acid reacts with a carbonate, like sodium carbonate, we end up producing carbon dioxide gas. Here's the molecular equation. Here's the total ionic equation. And here's the net ionic equation. I'm going to stop there because redox reactions are kind of a completely different subject. It's switching gears, in a pretty strong way. And so before we come back to class next Tuesday night, I would like you all to read the rest of the chapter for sure, because we still have quite a bit of content to cover. And depending on where we get, the following classes, we will work on some practice and getting ready for the second exam.